Introduction, Signal Processing, Techniques and Methods, TFT, Filters, Filter Banks, Signal Analysis and Reconstruction, Statistical Signal Processing, Parameter Estimation, Detection, Adaptive Filters, Neural Networks, Analytical Techniques. Example, Linear Algebra, Optimization, DSP, Hardware, Fast Algorithms, Architectures, Implementation, Applications. These for technical methods and then application signal processing. Okay. Then communication, radar, sonar, sensor arrays, multi-channel signal processing. Sonar arrays, information theory, speech and audio processing, image, video, multimedia processing, biomedical, bioinformatics. Speech and audio processing, samples in x-axis, y-axis, x of n, x of n and x of t. This is x of t, x of n, x of n. This is the this is sample, this is sample, this is also sample, this is time. Okay. Analog time, A, analog time, B, discrete time 4 kilohertz, quantized 4 bits. Here in x-axis, in analog time 0 to 250 in x-axis samples, y-axis minus 0.2 to 0 plus 0.2, sorry, plus 0.2, yes, analog time. In discrete time 4 kilohertz, in B samples 0, 50, 100, 150, 200, 250 samples. In x-axis 0, minus 0.2, 0, not 0, sorry, minus 0.2, 0, 0.2, x of n. Here also x of n. Okay. X not of n. Here xn. Okay, this is discrete Fourier kilohertz. This is the quantized. In here, in x-axis, time in second, 0, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. In the scale, in x-axis, y-axis, 0.2, 0, 0.2, x of t here, okay, in x-axis. This is the quantized 4 bits. Examples, compression MP3, interference suppression, microphone arrays, speech synthesis and understanding, wave field synthesis, spectral analysis, time, x-axis time, y-axis frequency. Okay, here B physics and 32 bar GB, the black rogue. Okay, spectral analysis. Here sensor array processing, radio, astronomy, seismic arrays, sonar arrays, synthetic aperture radar, synthetic aperture radar, sonar arrays. Okay, seismic arrays, radio astronomy, radio astronomy. Okay. Signal processing for communication, signal processing for communication. Example, multi-user, multi-antenna, MIMO. M for multi-user, another multi-user, multi-antenna. Here multi-input, multi-output. Okay, it means multi-user, multi-antenna MIMO communication. Okay, channel estimation, baseband receiver design, VDSL, cognitive radio, compressive sensing. Okay, here signal processing communication. Here analog to digital converter, source channel coder, XFN, digital to analog converter. This part information theory, signal processing. This part up to here. Okay. Okay. EJ e power j omega t from digital to analog gives to op amp, then transmitter antenna, then receiver antenna, then amplifier, then band pass filter, then e power minus j omega t. This is electronics. This is the electronics. These two parts electronics. This is a electromagnetism. Okay. This is a electronics. This is a H of T total. Okay. Here digital analog converter. Okay. Again I need analog to digital converter. Then got it. Then Y of N. Then this signal processing in digital signal processing from this digital signal. Then again conversion to analog. Then getting output. Example speaker. Channel inversion equalization. Parameter estimation, deduction, signal processing. Here signal processing. This is the information theory. Signal processing. Signal processing. This part full. This part full. Sorry, not here. This part full telecom. Okay. We consider mostly random signals as opposed to deterministic signals. Signals described by statistical properties, mean, variance, correlation, PDF, power, spectrum. Signals often modeled by filters, output of filtered white noise, prediction filters, minimize prediction error, optimal filters, Wiener-Kalman filter. Okay, minimize mean square error, adaptive filters, LMS, RLS, estimation of signal properties via filter parameter estimation, spectrum analysis, estimation of frequencies. Um, Here, the sinusoid buried in noise. Example, a noise in a music signal. Here, in time axis, 0, 20, 40, 60, 80, 100 time. In y axis, -4, -3, -2, -1, 0, 1, 2, 3. Here, noisy time, domain, signal. Here, normalized frequency 0, 0.1, 0.2, 0.3, 0.4, 0.5. In y-axis 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Here corresponding frequency domain signal. Two sinusoids buried in noisy music signal. Okay. Modeling. What is a good stochastic model to describe the signal? How do we estimate the model parameters? This is the modeling. What is a good stochastic model to describe the signal? How do we estimate the model parameters? Filtering. Okay. Filtering. In this here, can we filter the noise away? Reconstruct clean signal? Yes. How? We'll see. Spectrum. What is a good estimate of the spectrum? Resolution versus noise averaging. can we detect the number of sinusoid and identify the two frequencies. A signal is a function that maps a domain, often time or space, into a range, often a physical measure such as air pressure or light intensity. Signal is a function that maps the domain of often time or space into range, often a physical measure such as pressure, light intensity. A system is a function that maps signals from to its domain, its input signals into signals in its range, its output signals. Both the domain and the range are sets of signals, signal spaces. Thus, systems are functions that operate on functions. Audio signals. Here, sound equal to time times the pressure. Okay. Our ears are sensitive to sound, which is physically just rapid variations in air pressure. Air pressure. Thus, sound can be represented as a function. Sound is as a function. Where pressure is set consisting of possible values, air pressure, and time is set representing the time interval over which the signal lasts. Voice 0, 1 pressure. At 0, 1 represents 1 second of time. An example of such a function is plotted figure 1.1. Such a plot is often called a waveform. Waveform of a speech fragment. Time in seconds in x-axis. Point 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. Here minus 20,000, minus 10,000, 0, 10,000, 20,000, 30,000 in y-axis. This here waveform of a speech fragment. Waveform of a speech fragment. Okay. That is the data points are called sample. So we will draw the plot. Plot is called stem plot. Signals are said to be discrete time signals because they are defined only at discrete points in time. A discrete time, 1 second voice signal in a computer is a function. Computer voice equal to discrete time tends to integers, where discrete time this is this much. So is the set of sampling times 8,000 divided by 8,000. Here 0, 1, 8,000, 2 by 8,000. So 8,000 divided by 8,000. So time in second, discrete time representation of a speech fragment 0.188, 0.190, 0.192, 0.194, 0.196, 0.198 to 0.2. Here is the time seconds, time in seconds. Here in x-axis minus 10,000, minus 5,000, 0, minus plus 5,000, 10,000. So discrete time represented of a speech fragment. Continuous time signals are functions defined over a continuous interval of time, technically continuum in a set of reals. The audio hardware of the computer is responsible for converting the computer voice functions into function of sound, time to pressure. That the hardware which converts an input signal into different output signal is a system. Here, pure tone reels That is, we